Welcome again to the International Virtual Course, Geophysical Engineering Department, Faculty of Mining and Petroleum Engineering, Bandung Institute of Technology. This course is coordinated by Bapak Dr. Wahyudi Parnadi from Bandung Institute of Technology, Department of Geophysical Engineering. And today, we have the first session with Bapak Profesor Josaphat Tetuko. How are you today, Professor?
Hello. Yes, I'm very good. Yes, thank you very much for the invitation.
Okay, thank you. Thank you for coming. And today we will discuss about environmental remote sensing. Our moderator for today is Bapak Dr. Wahyudi Parnadi, lecturer from Geophysical Engineering, Bandung Institute of Technology. I think we can start now, Pak Wahyudi and Professor Josaphat. Can we start now?
Yes, okay, no problem. Yeah.
Yes, I think Pak Wahyudi will read the CV from Bapak Profesor Josaphat. Time is yours, Pak Wahyudi and Bapak Profesor Josaphat.
Yeah, okay, thank you, Harmita. So, my name is Wahyudi Parnadi, and now I act as a moderator of today's session. I'm very pleased to see you here and welcome all of you to this course. This 2 weeks international virtual course is about geophysical for engineering and environmental. Now, ladies and gentlemen, our speaker today is Professor Josaphat Tetuko Sri Sumantyo from Chiba University, Japan. To his curriculum vitae. Could you show the slide, please, Harmita? Yeah. Yeah, thank you. Professor Josaphat Tetuko is professor in Center for Environmental Remote Sensing, Chiba University, Japan. And he graduated from Kanazawa University and got a Bachelor Engineering degree from Electrical and Computer Engineering and Doctor of Philosophy from Graduate School of Natural Science and Technology, Chiba University, and Master of Engineering from Graduate School of Engineering, Kanazawa University. So he has expertise in microwave remote sensing, synthetic aperture radar, and microsatellite. From 2002 to 2003, he is a lecturer at the Center for Frontier Electronics and Photonics. And then from 2005 to 2013, associate professor in Center for Environmental Remote Sensing, and then from 2013 to present, he is a full professor and in Center for Environmental Remote Sensing in Chiba University, Japan. And Professor Josaphat has over 400 publications on Google Scholar and over 3,000 citations. So latest projects and publication of him: airborne circular ray polarized synthetic aperture radar, analysis and design of ultra wideband circular ray polarized antenna and array, a hybrid design method for thin panel transmit array antennas, and many more. So I think he has more publications. Now, before the presentation begin, let me inform how the presentation will be going on. First, Professor Josaphat will be invited to present the material. After that, there will be question and answer session, and followed by conclusion. And I hope Professor Yusafat can give conclusion remarks. Now, allow me to welcome the speaker, Professor Yusafat Tohoku Sumanto, to deliver his presentation. Professor Yusafat, the floor is yours.
Thank you very much to Professor Wahyudi for the introduction, and also to Ms. Harmita, yes, to introduce me for the as the speaker today. Yeah, today, okay, I want to. Could you share for me? Yes, I want to share my slide. Okay, yeah. You can see my.
Yes.
Okay, yeah. Okay, thank you very much. Yes. Today I want to give a short tutorial on the lecture. Yes, entitled Environmental Remote Sensing. Yes, and especially specifically for the synthetic aperture data on the SAR, yeah, SAR, image signal processing and the application. I think my lecture is 2 hours. Is very short. Yeah, actually, I'm always give for the 3 day. Yes, for the whole complete lecture. And I'm Josaphat Tohoku Sumantyo. I'm manage Josaphat Microwave Remote Sensing Laboratory, or GMRSL, in Center for Environmental Remote Sensing, Chiba University in Japan. For the detail of my activity, you can read from this website, yes, of my laboratory. The short biodata of me is like already introduced by Bapak Wahyudi, and yes, I'm now I have the journal paper 129 peer review paper, and then invited talk paper 264, and also the conference paper is 488. Yeah, I think totally more than 700 paper that I already published. Yeah, and then I'm right now is to be the leader of the IEEE Geoscience and Remote Sensing for the technical committee of instrumentation and future technology, and especially for the unmanned aerial vehicle and future technology, and also the associate editor of the IEEE Geoscience and Remote Sensing later. Today, I want to give the lecture. Yes, when the content is like shown here. First is about how to observe the planets. Yes, especially our planet is the Earth. Yes, it is very important before we start to discuss about the SAR image processing. And then the observation mode. Yes, using the synthetic aperture data on the SAR. And also after we get the data from this sum of the mode, especially I want to talk about the range Doppler algorithm, or RDA technique. Yeah, and then how to process the image. We call it the image basic processing, and then the because the image is actually in the unit is in the pixel. How to generate the pixel itself, it is very important. And then the characteristic of the image, and also the INSAR, it is one of the application. And then finally is if the time is still remain, is I want to talk about this application using the synthetic aperture data. Okay, before I start is I want to introduce my laboratory. Yeah, with the mate. Oh, wait. I think this one. Yeah. I think you heard the voice. Yeah. This is my laboratory, Josaphat Laboratory, or Josaphat Microwave Remote Sensing Laboratory.
Welcome to Josaphat Laboratory JMRSL. Josaphat Laboratory was founded in 2005 and affiliated in Center for Environmental Remote Sensing, Chiba University, Japan. We always serve the advanced science and technology on microwave remote sensing and contribute it for Earth monitoring and global community.
As the Chiba University motto, Josaphat Laboratory always aim higher to promote the advanced technology and science on microwave remote sensing field by holding international educations and research activities. Josaphat Laboratory also develops various microwave sensors, large-scale unmanned aerial vehicle or UAV, image processing, and its applications. Josaphat Laboratory has a complete facilities in microwave remote sensing field, for example, simulators, manufacturing facilities, anechoic chamber, ground test system, clean room, and microsatellites. We also develop unmanned aerial vehicle for ground test of our sensors.
Kami juga mengembangkan radar yang dipasang di pesawat Boeing 737
私は今、
Shen
遠頻波合成開口レーダーに搭載する信号生成装置をこの FPGA の基盤を用いて開発するという研究を行っています。幅広い分野においてたくさんの研究課題がある当研究室。もし興味をお持ちになりましたら、ぜひ一度お越しください。よろしくお願いします。
Thank you very much for your interest to Josaphat Laboratory. We always welcome all of you to visit and collaborate with Josaphat Laboratory.
Oke, mungkin sudah ada gambaran ya mengenai lab kami. Oke, saya lanjutkan lagi untuk konten hari ini. Oke, saya kira slide-nya kelihatan ya. Di sini sebelum kita mulai untuk belajar mengenai synthetic aperture radar, kita harus mengetahui dulu mengenai planet yang menjadi target untuk observasi atau penelitian kita. Oke.
Excuse me, Pak Yas, please speak in English.
Okay,
There
yeah,
are some foreign students here.
Okay, yeah.
Yes,
before we start to observe the planet itself, yeah, in this case is we need to know about the characteristic of the planets. So in this case is especially our planet or the Earth, yeah. So in this case is at least is we must know about the what is radius, yes, and also the weight on the gravity, and you can see from this parameter, yeah. And then it is in the distance from the sun, yes. It is we need this information to get the what is the sun illumination, yeah, because we put the solar panel on our satellite to get the the energy and the power, yeah, to operate our satellite, yeah. And then when we observe the Earth, yeah, it is we need to know about the velocity, yeah. And then here in the tilted axial angle, yes, and also this on the equator radius, it is very important, yes, because we need this information is when we design our synthetic aperture radar onboard satellite. We need this information because the sweat and also the range, yes, and the azimuth direction, it is very important parameter. And okay, this is the weight, and then the density is okay. The gravity is very important too, yeah. Next is actually if we observe using high frequency, it is have the effect on the what is some disturbance, yes, in the atmosphere. So in this case is you must know about the composition of the gas, yes, in the atmosphere, yeah. And okay, this is some of the planet that we know, yes. And then here is I'm sorry, sometimes it's mixed with the Japanese because I use this slide for my lecture, yes, for the in Japanese lecture. Okay, and here is, for example, we already designed our satellite is for the Earth and also for the Mars, yes, and also one is for the Moon, yes, because this, this parameter, yes, this at least in the radius is very important, yes, to know about the heat, yes, heat of on the altitude of our satellite to observe the planet itself. Okay, and I want to skip this one, and the most important is the Earth, yes, because it is the radius in on the equator, yes. You must please remember that the radius is 6,378 kilometer, and then at the polar, yeah, polar radius is 6,356 kilometer. It means the difference between the equator and the polar is about 21 kilometer. 21 kilometer is very big, yes, because we want to get the good, position every pixel. So in this case, is you must know the position of the satellite itself in the on the equator or in the subtropics or close to the polar area. Yeah. So in this case, is the resolution is to be slightly different. Yeah. When you observe in the equator, subtropic, and also the polar area. Okay, at least you can imagine about what is the important parameter that we need to consider when you make the observation. Okay, wait a minute. Okay, no, slide number 2. Okay, I want to talk little bit fast. Yes, because the slide is too many. Okay, next we want to talk about the observation mode. Yeah. When we do the observation using the synthetic aperture radar, here is you must know about the some mode of the observation. Yeah, it is very familiar. yes, in our field is the strip map mode. Yeah, the strip map mode is when you observe like this one. Sorry, wait a minute. Okay, when you observe, it is Jerswan Sar is one of the Japanese synthetic aperture radar onboard satellite. Yeah, that the antenna is the length is 12 meter, and the width is 2.2 meter. Yeah, and then the observation beam. Yes, it is about 1 degree. Yes, in the azimuth, and also about 5 degree in the range direction. Yeah, and then the width of the length of the antenna is 12 meter. It is I want to show you that proof that resolution on the ground is to be 6 meter. Yes, it is half of the length of the antenna at the azimuth direction. And then the range, the sweat. Yeah, the sweat here is W. It is 75 kilometer, and this one is based on the width of this antenna. If the antenna is 2.2 meter, it means under the this range direction beam width is about 5 degree. So in this case, is you can observe this sweat is 75 kilometer. I want to show you also this how to calculate this one later. And the speed of the satellite with the head is 568 kilometer. This is the speed of the satellite itself is 7.6 kilometer per second. It is very fast. Yeah, in a second is the satellite will move 7.6 kilometer. Okay, it is we call as the strip map mode. Yes, please remember. Yes, the name of this one. Okay, next. Yes. Okay, if we, it is in the cross section. If you cross on the azimuth direction. Okay, and in the strip map mode is why the synthetic aperture radar is put on the side. Yeah, so we call also on the side looking radar. Yes, because we put the antenna of this radar is on the side of the platform. Yeah, because the observation area. Yes, it is the we call it the azimuth. Yes, and it's here the platform direction, and here is the nadir, and here in the range. Yeah, so in this case is here we call and the slant range. Yeah, the slant range. Yeah, so because in the perpendicular direction, yes, the footprint, yes, in the perpendicular to the azimuth, here in the you can find that the Doppler line, yes, here is to be same. Yes, because if you observe in this direction, you can see here, yes, the Doppler line on the Doppler frequency is different. So it is a big problem for our observation. So in this case, is better you can find the perpendicular line where the Doppler frequency is same. So in this case, is we call this line is to be the equal Doppler line. So why the synthetic aperture radar working, it is we call in the side looking radar because this reason. Yeah, and the other one, this line we call also the equal distant line. Yes, because from this nadir it is equal. Yes, from this nadir. Okay, yes, and next is the screen mode. Screen mode is when the satellite is moved, the antenna of the SAR is we made, it is a circular observation. by using the circular vision compared to this street map mode. Yes, street map mode is if you observe, you transmit one pulse is to be scattered is just one times. Yeah, but if you use the screen mode, yeah, the screen mode is when the satellite is moved, you will observe on the forward. Yes, here in the forward, and then after through here, and then you can observe with using the backward beam. So in this case, it's twice. So in this case, is you can reduce the effect of the shadowing. Yeah, shadowing for shortening you can reduce using this technique. We call in the screen mode. Yeah. Okay, next is spotlight mode. Yeah, spotlight mode is when you move to observe is, for example, this area, it is fixed. You observe to pointing one area, and then move, and then you can get the scattering from just one area. So in this case, is the benefit of this technique is you can get the resolution. It's almost equal to the lambda on the wavelength. Yeah. For example, if you use the L-band SAR with the frequency 1.275 gigahertz, you will get the ground resolution is about 24 centimeter. It is very good. Yeah, compare if you use just street map mode. Yes, the resolution is about 15 meter. Yeah, it is almost tens. Yes, 10 times of the wavelength. Okay, inverse mode. Yes, inverse mode is the radar access is fixed, and then the object is to be calm and closer to the radar, and then you can make the analysis, and you can reconstruct the object surface or the object material characteristic and so on. Yes, we call it as the inverse mode synthetic aperture radar. And next in the Scansar mode. Yes, a Scansar mode is when move. Yes, it is we observe here. Yes, this area, and then move here as you observe here, and then move here, and then you can observe here, and then you can gather this area, and then when come back here, you observe the next of this area, and then you observe like this one. So you can get this observation area is very large. Yes, compared to the street map mode. Street map mode is just area, but here is transmit, then take a rest, or transmit, take a rest, transmit, take a rest. Yeah, but street map mode is will continuously to transmit the pulse itself. Yeah. Okay, by using the Scansar mode, you will get the observation area is more larger. Yes, compared to this we call it the street map mode. Yeah. Burst mode. Yes, we use this technique when you observe the area that is a deep, a deep surface space observation. You must keep the efficiency of the system itself. So in this case is you transmit and take a rest, transmit, take a rest, and then transmit and take a rest. So you can get a very long observation area, but unfortunately the resolution is to be dropped. Yeah, the resolution to be bad. Yes, so in this case is, but you can get a very large area. For example, of the burst mode, it is when the Magellan radar, yes, made the observation of this one is I think the Venus, yeah, the Venus area, yes, because the Venus area is covered by the cloud almost whole of the year. So in this case, is we need to penetrate the cloud. So in the but unfortunately, to save the energy is we use the burst mode technique. Yeah, this is also same. Yes, the volcano of the Venus. Yeah, I think it's, you can get the image of this. Some image of the Venus is from the NASA homepage. Okay, and the final one is the wave mode SAR. Wave mode SAR, if you want to observe the ocean, is very large ocean area. For example, the Indian Ocean, on the Pacific Ocean, Atlantic Ocean. Yeah. So in this case, is you don't need to observe continuously because it is waste of the power. So in this case, you can just observe, take a rest, observe, take a rest, observe, take a rest, and observe, take a rest. So in this case, is because the wave of the large ocean, it is almost the long wave. So if the long wave is, you can just get the data, and then you can mosaicing. Yes, you can predict that this area is almost same. So after you made the very long observation, is I think is you can make it's very large. What is the means on the average of the wave itself. Okay, yes, it is already okay. I introduced the mode of the synthetic aperture radar. Okay, yeah. Okay, now we want to talk. Here is the what is the most important part of the synthetic aperture radar. I want to talk about the SAR basic image processing. Okay, yeah. Okay, this SAR or synthetic aperture radar basic image processing. Yeah, here is in our laboratory, we developed the synthetic aperture radar for the UAV and high altitude platform system or hubs, and then for the aircraft, and also for the micro satellite. And some of book about the signal processing is you can refer from this book. Yes, from the here is I think it's many people use the Ian Chaming books. Yeah, and then from the system itself is you can refer from the synthetic aperture radar, and also processing of synthetic aperture radar images. And for the INSAR, yes, interferometric SAR, it is some application as you can use this book. Yeah, and then if you want to know about the SAR image processing using the MATLAB, is you can refer this book. Okay. Synthetic aperture radar is called also as the microwave sensor, and then the active sensor, imaging radar, and side-looking radar. Because this synthetic aperture radar, it is the from the satellite or some platform illuminates the microwave and receive a backscatter wave, and then process it to be in the image. Yeah. And then the benefit and also the weakness of the synthetic aperture radar, you can read here. And the benefit is we can operate in all weather because we can penetrate the cloud. Yes, and also we can operate in the nighttime. It's not just the day. Also nighttime if we can monitor. Yeah, and then high coherency of phase. We can use employ this information from the interferometric SAR and also differential interferometric SAR. And the other one is also from the polarimetric. Yeah, on the because the polarization on the polarized synthetic aperture radar on the pulsar. Yeah, so in this case is pulsar or synthetic circularly polarized synthetic aperture radar. This is my radar. Yes, I want to introduce to you later. Yeah, okay. And the weakness, unfortunately, to process the synthetic aperture radar, you must know about the at least is the electromagnetics. Yeah, in Indonesia is medan elektromagnetis or gelombang listrik magnet. Yes, in Indonesia. If you know this basic theory, is I think is you make more easy to know about the process in synthetic aperture radar. And then some distortion. Yeah, distortion is because you know, when we fly, it is on the side looking. Yeah. So in the side looking is when you observe some of the object with the head. So in this case is, so the object is to be tilted. Yeah, tilted to your platform. So it means we call the foreshortening. And then foreshortening and the back, you will find the shadowing. Yes, shadowing. Yeah. But sometimes it's also the we call it the layover. Yeah, layover is more terrible. Yes, because the object is to be opposite. Yeah. Okay, this is some of the Japanese satellite. I lost to Pulsar 2, and then the existing one is you can see some of the satellite here: CSAT, ALMAX, AIRS, JERS1, RadarSat, and VSAT, ELOS, TerraSAR, and also here is Microsat SAR. Yeah, CPSAR. This is my satellite. Yeah. And we also developed the synthetic aperture radar for the CN235 of the Indonesia. Yes, and we install the antenna. It is our original antenna that developed in Josaphat Microwave Remote Sensing Laboratory using the circularly polarized synthetic aperture radar. And we put here, and then the radar system is we put inside in this CN235 of the aircraft. Yeah, and this one is our first images that we got from our CPSAR. It is the first in the world of the circularly polarized synthetic aperture radar images. And you can see this one is the crossroad of the close to the airport of Hasanuddin, yes, at the Makassar, yeah, Makassar city. And you can see it is we got from the camera of the GoPro. It is covered by the cloud, and then our radar is very clear, no cloud here. Yes, and then we can observe. Yeah, is no cloud and no haze, and the data itself is very clear, with the resolution is 30 centimeter. Yeah, and it is in the full polarimetric images of our CPSAR. Yeah, and you can see here is LL, RL, LR, and RR. R is mean right-handed circular polarization, and L is left-handed circular polarization. You can download our paper in IEEE JSTAR. Yes, it is free of charge. Yeah, and you can find the theory and also the system of the circularly polarized synthetic aperture radar. Okay, and I want to show you about when we did the flight test in Makassar. Yeah, wait a minute. Yes, this is when we did the flight test. Okay, we developed LCX band. Yes, for the microsatellite Cessna. This one, like this one, is we put for the Cessna. Yeah, and then we did the flight test at Yogyakarta. Yes, Lanut Adi Sucipto. You can see here in the radome under the belly of the aircraft, and we did the flight test. Yeah, and the radome is it is also our original material that we developed. Is very light and very strong. Yes, of the material. Yeah. Okay, after we did experiment at Lanut Adi Sucipto, and then we start experiment at Lanut Hasanuddin. It is our X band from the Boeing 737. Yeah. And next is C band synthetic aperture radar. Yes, this one is from the CN235 aircraft. Yeah. Yes, it is when we did the flight test, you know, even as many cloud, we want to prove that our radar can penetrate the cloud. So in this case, it's all weather. Even rainy, season is we can operate this radar. Yes, and you can get the information of the ground surface and also a little of the underground. Yeah. Yes, you can see, you know, it is many cloudy. Yes, a cloud. Yeah, and the image is of the CPSAR, as you can see underground. Yeah, it is here is more clear. Yes, no cloud. Yes, and it's very clear. Yeah, and then in this image is you can get the information of the intensity, phase, and also the polarization. Yes, and in this case, it's full polarimetric. Yes, or full polarization. Yeah. You know, even it's cloud is very clear. Yes, our images. Yeah, it is in the Hasanuddin airport, and the test site of our radar is we met at the edge of the runway. Okay, this is for the calibration. After that is we did the application test. Yes, we flew at Biringkasi, this one Biringkasi seaport, and also the Pangkajene area. Yeah. And the right side is our images. Yes, we can observe the some ship. Yeah, ship is clear, no cloud. Yes, and then we can also combine with the AAIs. Yeah, so the position of the ship, and we can detect using our system. Okay, next is it is in the paddy field area and the interface with the ocean area, and then we met the flight. Yes, it is close to the Pangkajene city at the south of the syllabus. Yes, or Makassar. Yes, it is in the city of the Pangkajene. Okay, yes, it is our flight test. That yes, I think is it is in the first in the world. Yes, for the synthetic aperture radar, especially in the circularly polarized synthetic aperture radar. Okay, I want to continue my slide. Yeah. Yes, next, after we finish to develop on the aircraft, and then now we develop on the microsatellite, and I hope we can launch as soon as possible. Yes, and now our student, yes, from many countries, yes, from Pakistan, Indonesia, Brazil, and also from the Malaysia, of course, from Japan also. Also existing in my laboratory to develop together, and then compare between the optic sensor and the synthetic aperture radar. You can compare. Yeah, there's you can see here. Yes, it is in the optic sensor. It is in the area of the Sahara Desert. Yeah, you can just find the surface information. But if you use the synthetic aperture radar, you can get the underground information. Yeah, I think if you working in geophysics, yes, it is very important use the synthetic aperture radar because we can penetrate underground. Yeah, so in this case is you can find it is the underground river network. It is inside the Sahara desert of the Africa. Yeah, it is in the northern part. Here in the Egypt, and here is Somalia area. And then for the details, you can read our paper in International Journal of Remote Sensing. And the information of the phase, yes, you can also employ for the interferometric SAR to know about the land deformation. Yeah, so I made the observation of the Bandung city, and then you can also read this observation result. Yes, here is from my paper in IEEE TGRS. Yeah, and also the here is very simple, just using the intensity. Even using the intensity, as you can get the mapping of the burn peatland, yes, at the central of the Borneo or Kalimantan. Yeah, this is you can read my paper from the detailed technique in International Journal of Remote Sensing. Yeah, and optics. Yes, the optical is very easy. Yes, recognized by our eyes. Yes, because the wavelength 0.4 until 0.7 micron. Yes, we can get by using our eyes. Yeah, and easy to understanding. Yeah, but unfortunately, in the SAR is wavelength is very long. Yes, more than 30 centimeter. So in this case, it can penetrate, our eyes. So you cannot recognize. Yeah. So in this case, it's very difficult to understanding. Yeah, but right now it's many software and many technique already established. So you can use this technique. Yes, for some classification, especially in the geophysics field. Yeah, and then here in the wavelength in order a centimeter is very long. Yes, and then mechanism of packet scattering is very complicated. Yes, in this case or complex. Yeah, so in this case is you must know about the polarimetric SAR. Yeah, in the polarimetric SAR is you can get the parameter of the scattering, at least is 4. Yeah, surface scattering, volume scattering, double bounce, and also the helical. Yeah, helical scattering. Yeah, 4 of the scattering. Yeah, this is already established, so you can learn about this 4 type of the scattering. Okay, and distortion in the image is caused by the observation technique. Yes, it is so based on the observation technique. You can modify or revise, yes, and calibrate this images. Okay, next here is CPSAR or SAR is, can penetrate the cloud. Yes, this is from my sensor. This is Makassar city. Yes, optical is covered by some cloud, but synthetic aperture is can penetrate. Yeah, and also here is the volcanic ash. Yeah, this is can be penetrate using our sensor too. Yes, but optical images is unfortunately we cannot penetrate the cloud. Yeah, on the volcanic ash. Yeah, and on the synthetic aperture radar is we can express our phenomena of the wave propagation is using the here in the time change. Yes, on the spatial change. Yeah, if we talk the time is the electric field. I think we use the electric field. Even we have the magnetic field. Yeah, but it is we are familiar with the electric field. So this case is if the time if moved, so the electric field is also moved too. But when you saw using this two-dimension of the graph, so in this case is you will find that the wave is will rotate yes, on the center here. Yes. So in this case, is even in the spatial location is moved like this one, you can also express using this very simple one. So in this case, is the real and imaginary of the SAR signal is you must know and get. Yeah. So in this case, is please remember here the wave expression is we can express using the exponential 2 pi IFT. F in the frequency, T is the time. Yes, and then I is the complex. Yeah, so the imaginary part of the complex. Yeah, so at least is it is this equation is depend on the frequency and the time. And if you want to extract the frequency, you can just make the derivation of the phase. Yeah, pi. Yes, here is using the time. Yeah, this derivation is you can get the frequency itself. Please remember exponential 2 pi IFT. Yeah. And then the microwave is classified by several of the zone on the band. Yeah, we start from the UHF. Yes, the frequency is about 0.3 to 1 gigahertz. Yes, and the wavelength is about 300 to 1,000 millimeter. And then the larger one is the frequency is 40 gigahertz, and the wavelength is 7.5 millimeter, and we call it as the millimeter wave. Yeah, and you can see here it in the atmospheric penetration. 100% is mean 100% penetration. So you can see here, and the microwave is can penetrate the atmosphere. Yeah, especially the cloud. Yes, this is the frequency P until Ka. Yeah, P L S C X K U K. Yeah, band. Yeah. Okay. Here is the reflection and also the penetration. Yeah, I think it's when you learn in junior high school or high school, you already know about the penetration. Yes, when the wave is come here or inside, yeah, incident. We call it here in the incident angle, and then if the surface of the medium of the object is smooth, so you can get the reflection angle. It is almost same with the incident angle, but the penetrated wave on the penetrated angle here is depend on the medium of this object. On the image of the synthetic aperture data, sometimes you will find it's very dark, yeah, a dark area. So why is it dark area? It's because the mirror reflection, yes, from the satellite will scattered by the surface of the ocean and then go back to the to the satellite again. And but unfortunately, some part of the signal is go scattered to another direction. Same with you can see here is the ocean area close to the Anak Krakatau. This area is to be black because the scatter is go go too far away. It's not come back to the satellite itself, but some area is come back to the satellite because it is in the roughness is I think is very high. So we can get this scattering from this island. Yeah, but some part is to be black. Yes, because it is in the shadowing. Yeah, shadowing phenomena. Okay, and the effect of the surface roughness. Yes, we define using the Rayleigh condition. Yes, the equation is you can see here. It's the height of the object. Yes, here is less than lambda divided by the h times cosine theta. Cosine theta is the incident angle. Yeah, and then lambda is from the L band. Just one is 23 meter, and then the incident angle 38 degree. So if you insert here, and you can find this h is almost 4 centimeter. If the height is 4 centimeter, yes, it is less than 4 centimeter is to be in the smooth, yeah, smooth. And then when the incident wave is come, it is will scatter to another direction. So in this case, is does not come back to the satellite, and this area is to be black, yes, a black response, yeah. And then if the the height of the object is larger than 4 centimeter, it is to be in the slightly rough surface. So this the scattering is to be some part is go back to the satellite itself. But for how about the rough surface? If the height of the object is large, yes, compared to the 4 centimeter, so then the scattering to the satellite is very strong. Yeah, and you can see here it is smooth. Smooth is the mean the smooth surface is scattered is very low. Yeah, because go to another direction. And then slightly rough surface, yes, and the other one is rough. It is very rough. You can get from the image of the synthetic aperture radar of JERS-1 around this mound of the Krakatau. Yeah, and then it is if the scattering is different in the time, because the time is different, and then the season. Yeah, here is for example is 2011 February. It is the winter season. Yes, and then it is 2010 fifth month. It means May. Yeah, it is I think it's growing. Yeah, some of the vegetation is growing, and you can compare in the winter. Here is to be more bright. Yes, because the tree is already growing up. Yeah, and then this area is also the tree is mixed with the here in the sand. Yeah, the sandy area. Yeah. And I think some part is to be affected by the vegetation, yes, during the summer, yes, and also close to the autumn, yes, it is still some of the vegetation is existing. Okay, and the scattering itself is we can classify at least as the surface scattering and volume scattering. This scattering is because the difference of the dielectric constant, and also multi-scattering inside, in the object itself. Yeah, we call multi-scattering is to be the volume scattering. If you want to make the modeling of the object, yes, you can make, for example, it in the tree, and then it in the scattering incident waves when come. The first thing here in the scattering of the surface scattering, and then some part is to be penetrate to the object, yes, on the tree, and then it is to be multi-scattering inside on the tree, and then we call this scattering is to be the volume scattering. Yeah, because many times scattering inside the tree on the medium, and then some part is to be go out and scattered by the land surface, and then scattered and go back to the satellite and to be the surface scattering. Same when you want to observe the icy river here in the surface scattering, volume scattering, and surface scattering. And then from the dry and also sandy area, I think it's like the I think it's Lapindo, yes, at Sidoarjo, and also some part of the NTT at Sumba is very dry. Yes, you can make the modification like this one, and also some area of some geophysic phenomena is like the Blue Duku, yes, at close to the Cepu and Blora. Yes, I think it's always spouted of the oil, yes, raw oil. Yeah, so in this case, I think also affected to the area surrounding of this the phenomena. So in this case is because it's dry, you can combine using this surface scattering, volume scattering, and surface scattering. This is my theory when I made the analysis of the pit line. Yeah, and the pit line is why the pit line is can burn, yes, and then made the forest burning and Borneo area. Yeah, I made the theory of like shown here. It is in the incident wave and surface scattering, and go inside here, and many scattering is to be in the volume scattering, and then some part is go out and go back to the satellite, and we call as the surface scattering. For the detail, as you can read my paper in International Journal of Remote Sensing, and also the GSPRS, yeah, Japan Photogrammetry and Remote Sensing Society. Yes, I employ to observe the pit line burn in central of Borneo. And you can see here in the plane wave, yeah, and the plane wave is here, and it in the surface scattering, and then you can see here is many scattering here. Yes, we call as it is to be in the volume scattering. Yeah, it is when we want to what is show about the combination of the wave scattering. Yeah. And I also employ this technique for the environmental observation. Yes, to observe the tree. Yes, especially here in the diameter of the tree. And then yes, you can read my paper in International Journal of Remote Sensing that I made the estimation or classification of the Rasamala tree of the Gunung Gede Pangrango. Yes, at West Java. Next is the polarization. Polarization is classified to be the co-polarization and cross-polarization. Co-polarization is if the transmitting wave and receiver wave is same. For example, HH or BB. And cross-polarization is transmitted wave. For example, this one is transmitted V and received is H. And here is transmitted H and received is V, opposite. Yeah. So in this case is, but actually here is depend on the aerospace agency. Sometime in the aerospace agency is defined that, for example, HV, it is H is to be transmitter and V is to be receiver. Yeah. Here is please be careful when you want to use the polarimetric image of the synthetic aperture radar. Yes, it is the vertical polarization, and here is the sorry, yeah. Okay, here is vertical polarization, horizontal polarization, and here in the circular polarization. Yes, left-handed circular polarization. Yeah. Okay, if you want to know about how to simulate this, in time domain, you can refer my books. Yeah, Metode Beda Hingga Kawasan Waktu is published by the ITB. Yeah. And it is the application to observe the Rasamala. Yes, Rasamala is the main tree in Gede Pangrango Mount. Yeah. It in the result. Yes, I made the modification, and yes, almost match well with the ground survey result. Yes, and it is my paper in International Journal of Remote Sensing talk about the classification of the tree. Yes, in this area. Yes, next is the pit line on the forest burn. Yeah, using the Scansar images that got in 1997. Yeah, and you can compare with the optical images. It is before the burning, and it is after the burn, and we made the ground survey, and then collected the images and collected some sample and measure the dielectric constant in my laboratory, and then put the parameter, because the dielectric constant is having the relation of the epsilon, yes, or dielectric constant, and also mu, yes, permittivity, and also the sigma, yes, sigma is the conductivity, yeah, or the characteristic of the conductor. Okay, and then the result is you can find here is the thickness of the burn core seam and also the backscattering coefficient, and you can get, if the burn core seam thickness is larger, it means to be short, and then the backscattering is to be, a drop. Yes, like shown here. Okay, it is already explained. And the system itself is, but the scattering is, many scattering that you must know about. For example, HH, HB in the dry land and also in the wet land. Okay. It is some scattering of by the Magellan mission at the Venus. Yeah, I think it's okay. This is for the basic of the SAR image. Okay, next, I want to continue. Yes, this one is how to generate the pixel. Yes, pixel of the synthetic aperture radar. Okay, the history of the synthetic aperture radar is started from 1953. Yeah, it is by Carl Wiley. Yes, and then development of the civil application, and then the first satellite on board SAR is by the CSAT. It is the NASA. After that is by the ALMAX. Yeah, and then Europe. It is S1 and also S2, and then Japan is to be JERS1. Yes, after that is ELOS and ELOS2, and next is to be ELOS4. Yeah, and then RadarSat is by the Canadian Aerospace Agency, SRTM is by NASA and Germany, and then NVSAT by the ESA, and ELOS is by Japan, and then here is the TerraSAR X by Germany, DLR. And here is LS2 Japan, and Sentinel-1A is by Europe, and 2016 is by the also same Europe Aerospace Agency launched Sentinel-1B. Okay, this is some of the summary of the satellite, and here in the airborne SAR, and yes, it's in the history of the CSAT, yeah, and ALMAX, yes, and here in the ESA, yeah. And the story of the SAR image is in 1960. Yeah, they work using the analog technique. Yes, in here in the analog, it means the optical technique processing method. After that is in 1970, it started using the digital processing. Yeah, but unfortunately, it's still in 1980 in the CIRB, it is NASA mission is using the optical processing, but then they changed to be in the digital processing. In 1990, the optical processing is still used by the some Russian, Russian, but they made the hybrid, combined with the here hybrid combined with the digital. But another mission like the ERS-1, RadarSat, Series C, EOS SAR, and another is use the digital, already using the digital. And then in 2000s, yes, mainly employing the digital processing. Yes, so in this case is until right now, because many computer, like in my laboratory, we also use processing the synthetic aperture data image using the digital processing. It is the first image of the, I think it's here in the California, yes, Bay, and you can see it in the raw data. Yeah, the raw data after we made the range compression and azimuth compression, is you can get it is the first image of the CSAT. Yes, here in the area of the California. Yeah, I think it's here is maybe the Los Angeles, yeah, area. In this process is we want to process from, you know, when we observe, because we move, yes, the aircraft is moved, we transmit the pulse and many pulse, because in 1 second we transmit from the JERS one is 1,500 pulse. Yeah, so in this case is you can get the response, you know, because the satellite it move like this one, the response from the 1 point is to be like the block like this one. For the process is first you must do the range compression. Yes, and you can get, you know, this direction is range, so you must make the range compression and you can get the line like this one. And after that is you must do the azimuth compression. The direction is azimuth. So after you make the azimuth compression and to be in the 1 point, you know, here is 2 dimension, 1 dimension, and then here is to be 1 dimension, but point, yes, point is not the line. Yeah. For the SAR image processing, digital, yes, here is many technique. Yes, one is using the spectrum analysis method, like the DRAM methods, and then the correlation technique. Yes, in this case is the frequency domain or time domain. Yeah, I think it's in the frequency domain is more efficient for the memory. Yeah, but unfortunately it's a little bit complex of the technique. And I think the most easier one is the using the time domain. Yeah, because the time domain is you can get the range is very easy. Yes, and also the pixel is very easy. Yeah, here is a 2 method, 2-dimension algorithm and range Doppler algorithm, or we call it the RDA technique. Yeah. Okay, for the RDA technique, you must know about this. You know, it is in the geometric system of the flat ground. Yeah. So in this case, is here I already explained in the beginning that here in the range, and here in the nadir, and here is the slant range. Yeah, the slant range. Yeah. Okay, and the width here 5 here azimuth beam width, and then here in the range beam width. Yeah, the range. Yeah, and also the azimuth beam width is very important, because look like our eyes, if you see on the center is very clear, but unfortunately here is to be, you know, in the edge here is I think you cannot see what is the object. Yes, in the side of here, and also in the back of our eyes is, I think you don't know. Yeah. Okay, and the point here in the antenna and here in the nadir, yeah, nadir, and here in the target itself, we want to derive this pixel. Yeah. Okay, I skip this one, and here is when we want to decide the beam width. Yeah, the beam width is the lambda divided by the length on the width. Yeah, for example, here in the range. Yeah, in the range it means the sweat width. Yes, sweat width is alpha. Yeah, it's alpha is here is lambda is 24 centimeter, and divide by b. Yes, b is 2.2, and you can get later that the area is 75 kilometer. Yes, it's very large. Yeah, and also at the azimuth direction. In the azimuth direction is you can you know, lambda 24 centimeter divided by the 11.92 meter. Yeah, so in this case, you will create underground, yes, you will get about 14 kilometer. Yes, 14 kilometer. Okay. Yes. From the antenna itself is I want to skip. Yeah, it is some antenna that already operated by the JAXA. Yes, from the satellite GERS-1, and here is from the PISAR. Yeah, of JAXA and ICT. And here is the antenna for the ELOS, Japanese ELOS-2. Yes, and here is the antenna for our UAV, and we call it the circular polarized synthetic aperture radar. It is from the L-band. Yes, L-band. It is in the antenna from the ERS. Yes, European Space Agency, and here in the antenna that developed in my laboratory. Yes, I think many type on the antenna. Yeah, and we can combine. And the antenna from the telecommunication is we also develop here. Yes, for our UAV. Here's my anechoic chamber to test the microsatellite and also some communication devices in our center. Yes, we made the experiment in my anechoic chamber. Okay, it is in the coverage. Yes, when you observe, yeah, in 1 second. 1 second is we transmit 1,500 pulse. Yeah, it is in the response from 1 pulse. Yes, for example, you want to observe one object here, and this antenna is moved, and you can get this, this tracking area is like this one. Yeah, and this point actually is to be in the response of the sync function. Yeah, sync function. Yeah. So in this case is the image is to be in the block, like I already explained to you. From the block is you later you made the analysis, and you can get just the line, and from the line is you must to compress. Yes, after you compress is you can get the SAR images. Yes, it is in the radar equation. Yes, when you made to calculate the synthetic aperture radar, you must calculate how many power that you must transmit and scatter by the object with the radar cross section is how many, because the radar cross section is very important to decide. For example, you decide minus 35 dB or minus 20 dB or minus 20 dB. It is depend on what is your project itself, and then you can get the power, and then you can predict that if you fly how many kilometer and you need how many watt you want to transfer. Okay, it is when we want to design our system. Yeah, you must know about the here in the attenuator, and I already explained to you. Yes. Okay. Yeah, it is when you made the calculation. Yes, or analysis is it is in the example that I made the observation of the Cepu area. Yeah. Here is I think if we supervise one of the student in geophysics department of your department is in 2005. Yes, we used this technique. Yes, to analysis. It is the raw data. Yes, of the Cepu area. Yeah, and then you made the we call as here is the range compression. After we made range compression, is you will get is very clear image. We call it here is the, it is a single loop complex. Yes, single loop complex. Because in single loop complex is you still have the intensity of phase and also the polarization. Yes, polarization. We call this one is range Doppler algorithm, or RDA. Yeah. Okay, and if I enlarge is like this one, I think it's very easy. Yes, using this synthetic aperture radar to know about the lens situation, because this technique is, synthetic aperture radar is free of the cloud. Yeah, and you can get you know, the land information, and also the coastal area, and also the ocean area. Okay, yes, because the time is not so many, I want to skip. Yes, here is the pulse that we want to transmit. Yeah, the pulse we call it the short pulse. Yeah, and using this a convolution, yes, this convolution technique, and you can get, you know, it is in the scattering from the object A, B, C. It is if mix the response from A, B, C object, it is a big problem for us. So in this case, we need to make the correlation function. Yes, this correlation function is you know about the transmitted pulse, and that's just compare to find the how many dB of the correlation. Yeah, between your we call in the reference function. Yeah, reference function or reference signal, and receive pulse or scattering signal. And then you make the correlation, and you can get, you know, it is very clear that it is the scattering from the object A, and the green is from object B, and the blue is from the object C. So it is more clear compared to this, you know, the pure scattering wave from the object. Yes, here in the range compression, from the range compression is you will get that resolution is to be 17 meter. Yes, it is better than compare if you use the real aperture. Real aperture is 14 kilometer. Yeah, in the resolution, but here you can get is 17.4 meter. It is more better. Yeah. And yes, better use in FFT or frequency domain. Yes, the process, because if correlation function is just use the time domain, you must multiply using the summation is consuming the time. So in this case, if you use the in frequency domain, it is more faster, because you can just multiply. It's not summation. Yes, here in this to be in the summation. Here in the multiplication is just one component of multiplication. So it is very short. Of course, the time to convert using the FFT is consuming time too, but compared to the pure correlation function, it is more better. Yes, using the FFT. Okay, and the azimuth itself is, if no, you know, no compression, is you will get the resolution is about 14 kilometer. It is very big, and then we propose using the azimuth compression, and you can get the resolution is not 14 kilometer, but depend on the width, on the length of the antenna. For example, the antenna here is from the JERS1 is 12 meter. So the resolution on the ground is to be 6 meter. Yes, this is depend on the Doppler effect. And of course, you can also prove using the synthetic aperture radar technique, and you can get also the resolution of the ground at the azimuth direction. It is to be half of the antenna resolution. Okay, yes, and finally, you can get the reference function of the azimuth and range is almost same. Yes, even the parameter is different, but the shape of the reference function, yes, it is same. Yeah, and the other one is you must consider about the range migration. Yes, here is the range walk and range curvature. Yeah, if you get the image like this one, yes, from the response, it means here in the combination of the error of the range walk and also the range curvature. Range walks itself is when the satellite is moved at azimuth direction, the object of the on the ground is depend on the Earth rotation, because when we observe also the Earth is rotate, and we cannot stop the Earth. Yeah, so in this case, in the object is look like move like this one. So because this one is range walk. Yes, range walk phenomena. And next, range curvature. Range curvature is when you observe here in the, when you save the scattering, for example, from this point, is you save n to be here, and you move and you save it to be here, and the closer one is this one. So here you will get the curve like this one. We call it the range curvature. Yeah, and then a combination of the range walk and range curvature is to be the range migration. Yeah, this range migration is you must make the revision. Yes, you can use this technique. Yeah. Okay, and it is about the correction, and finally is very important too is about the multi-look. Yeah, multi-look is to reduce the noise. Yeah, the noise inside the images. So in this case is for example this L is about the the final resolution. Yes, so you can divide to be by 4, and it is the antenna 1, 2, 3, 4, and then you can observe and meet the average. Yeah, average. When you observe the first time is the resolution is better, but after you make the multi-look, even the noise is dropped, but unfortunately the resolution is to be bad. Yes, because to be 4 times of the good resolution. Yeah, it to be worse. Yeah, worse. Yeah, because 4 times. Yeah. Okay. Yes, and I want to move to the application. Yeah. Actually in the character, but unfortunately, yes, the time is not so many, but maybe we can talk later. Yeah. Okay. Yeah. It in the application of the synthetic aperture radar. Yeah. I think you study in especially in geophysics. Yes. I think you know very well about the condition surrounding of the Indonesia. Yeah. Now in this area is it is in the volcanic area, and we call as the ring of fire. Yes, because many magma on the volcanic activity. Especially I'm living here in Chiba, close to the Tokyo, and here is this island is composed by the volcanic, yes, activity. And Indonesia also same. Indonesia, we have 129 of the active volcano, and almost every day is some of the activity on the volcanic and generate the disaster. Yeah, and it is very what is famous in Japan, the Tohoku Earthquake that happened in 2011, and then within a couple of minutes, yes, the land is moved. Yeah, move 4.4 meter. Yeah, you can imagine your house is moved to another, a neighbor. Yes, and the next person, a property, 4 meter. 4 meter is very big. Yeah, and even in our area, Chiba area here in Tokyo, yeah, Tokyo is also moved 20 centimeter. 20 centimeter move. Yeah, almost all of the plate, this island of Japan. Yeah. We can use the synthetic aperture radar, and we observe, and then you can get it here in the interferogram. Yeah, and then after unwrapping, and you can get, and the edge here is 3.5 meter, and the edge here is to be 4 meter. The land is moved. Yeah, And here in the Chiba area is about the blue one. Blue one is about 0.2 meter. It means about 20 centimeter move. Yeah. And also I made some observation of the volcanic activity in Indonesia. Yes, here is the Mount Merapi, and yes, I made to observe the volcanic material volume change. Yes, from using the technique of the DINSAR, and yes, I got the best paper in one of the IEEE and IEC conference. Yeah, and yes, this is you can find the ground situation after the Mount Merapi eruption. Almost is the tree is burned, and also the some houses is covered by the sedimentation of the sand. Yeah, and then I made the classification using the synthetic aperture radar. Here in the optic sensor, you can just know about the surface of the lava here, and also the volcanic ash covered surrounding of the Mount Merapi. Yeah, and then here is the some photograph of the ground survey. It is in the TV brown tube. Yes, it is melting. Yeah, and also in the radio also melting. It is mean it's very strong and very hot or high temperature. Yeah. Yes, now we want to know about which area is deformed and which area is constant. Yes, using this technique. Yes, differential interferometric SAR. For this technique, is you can get from my paper at TGRS from the theory. Yeah. And then, yes, here in the result from the observation using the ELOS pulsar data, and you can unwrap, and you can get here in the real deformation. Yes, in centimeter. Some area is deformed 15 centimeter, but some area is you can find here is about 14 centimeter. Like here is you know the Mbah Marijan house is around this area. So it means Mbah Marijan area is covered by the magma or some volcanic ash. Yes, is about 14 centimeter. Yes, 14 centimeter is like this one. Yeah, it means I think it's strong, strong eruption that made this area is covered by the volcanic ash. Yeah, but it is you can get some information in very detail. Yes, detail is you can see here. Plus is mean sedimentation, but here is the green. It means deform, or because after eruption is some area is to be subsided or subsidence. Yeah. Okay. Yes, we made the ground survey like this one. Yes, and then based on the comparing to the ground data using the GPS, and yes, the average of the error is 0.2 centimeter. And then I also made the classification based on the villages, yes, this area, and then you can get, it is in the coverage of the area is the Pakem, city is more terrible. And then here is the, yes, it is in the sedimentation area. Yes, and the Pakem city is very, what is on the volume. Yes, I extracted the volume and get, yes, is very strong. Yeah, and also here, yes, this area is like the Jerakah, yeah, Jerakah and Tlogolele here, and I think it's Mbah Marijan houses is in this area. Okay, yes, another one is it is the why in Indonesia is many disaster is I refer from Professor Robert yes Hall, and you know, because this area is from 50 million years ago is composed like this one. Yes, just you know, Java and Sumatra is connected, but unfortunately now it's spirited, and here is Toba. Yes, now is to be you know merged. Yeah, and here in the Sulawesi. Yes, Sulawesi from the south part and also from the north part is to be you know connected in 2 million years ago. And here is Bali Island and Nusa Tenggara is appear in 15 million years ago. Yes, and then now is you know Papua Island is to be part of the Indonesia in 4 million years ago. Yes, and in the future, I think it's Indonesia and Australia is to be, you know, one area. Yes, and yes, I don't know. Yes, Indonesia is to be Australia or Australia is to be Indonesia. Okay, this phenomena is you know move almost every day. Yes, it is moving, and this moving is you know will release the power. This release of the power is will generate the earthquake and also the volcanic eruption. Yes, and also some fault. Yes, active fault. Yes, made some you know disaster like the landslide, and also some of the you know crack. Yes, crack on the fault. Yeah, and this one generated also the Aceh earthquake. Yes, and then we can observe using some of the remote sensing images. Yes, in the Aceh earthquake is like the Nias Nias Island also, you know, to be uplift. Yes, uplift about 2.5 meter. Yeah, and of course we can also using the synthetic aperture radar. After that is the Central Java earthquake also happened. Yeah, and then we observe using the synthetic aperture radar, and you can get like this one. It is very easy, just using the correlation coefficient, and you can get you know the red one is the collapse. Yes, collapse of the building. Yes, you can observe using two images of the synthetic aperture radar, just to extract the intensity. Yes, of the slave and the master. Yes, before and after the earthquake. Yes. And then it is the Lapindo. Yes, at Sidoarjo in this area. Yes, it is before the accident. Yes, hot mud flow, and here is after the hot mud flow. Yeah, right now is this highway is moved. Yes, to be turned like this one. Okay, yes, I made the study from 2006. Yes, in this area. Yes, and I observe. Yes, using the synthetic aperture radar and to know about the subsidence around this area. Yeah, in this case is yes, I publish in Compass. Yeah, in the center is 2.4 meter of the subsidence. Yeah, and here is the Compass, and you can read. Here's my name. Yes, and Chiba University, and here in the subsidence area, and the center is 2.4 meter, and around here is I think it's about 1 meter subsidence is happen. Yeah. Okay, and the other one is about the monitoring of the Bandung city. Yes, yes, I got also the award. Yes, from the size. Yes, it is one of the society in Japan. Yeah, and yes, I publish in IEEE TGRS, and to be, you know, it is in the coverage of the magazine itself. And the theory is you can find in this paper. Yes, but how to find the subsidence and the uplift. Yes, on the horizontal movement. Yes, dx, and also the vertical movement, dz, or here plus or minus. If plus is to be in the uplift, and if minus is to be in the subsidence. Yeah. Using two images, yes, you can decide as the slave and also the master. Yeah. Okay, yes, for the details you can get. Yes, here in the Bandung city, Cimahi area, Dayuhkolot, and here is about Cimario area, because I born at here. Yes, Lanut Suleiman. Yes, yes, I born here. Yes, and then grew up in Solo. Yeah, and yes, and this area is we made observation using the synthetic aperture radar, and here is Majalaya and also in the Ranca Ekek area. If we consider about the geological history, yes, in this area is the lake deposit, yes, because Bandung is composed by the or what is construct by the lake, yes. So in this case is here in the lake deposit, and here is the some of the tuff, yes, and here is some of also the some strong some of the composition, yes, of the geological composition. And based on this one is having the relation to the result. Yes, you can see here I made the observation since 1993 until 2006. But yes, of course we can continue. And you know, in the center of the Cimahi, yes, Cimahi city is always subsidence. Yes, I think until right now is still subsided. Yeah, and if you go to this area and the building, yes, like shown here, yeah, some wall is cracked, yes, horizontally and also vertically. Sometimes it's you know diagonally like this one, and some of the railway is also bended, is like this one, and this houses also are cracked, yes, and some areas the houses also subsided, and here's the irrigation building also cracked like this one, and you can see here in the road also a crack and wall also crack. Yes, it is yes a very pity condition of this area. Yeah, and then yes, I made the yes observation, and yes, almost match well that we derived using the INSAR and also this GPS. Yes, we what is compare. Yeah. Okay, and here in the fault area, we work together with some of the university in Malaysia and to observe the fault close to the, here is the you know, it is the KLAI, Kuala Lumpur International Airport, and unfortunately is crossed by the active fault. Yes, every year is almost 6 centimeter moving. Yes, in this area. And yes, it is from 2008, 2009, and also 2007, 2008. Yes, almost every year. Yes, this what is the fault activities occur in this area. Jakarta City also, you know, subsided. Yes, some areas we observe. Yes, 2007 to until 2008, and this area is you know, you can what is enlarged in the northern part of Jakarta. Sometimes you know the city is the road is fault, and also the bridge. Yes, it is some accident is happened. Is I think it is caused by the subsidence, because every year 6 centimeter move. Yes, it is I think it's very big. Yes, and made, you know, you can calculate this, the road will, you know, collapse in any year, as you can predict, yeah, using this technique. Yeah, and here is yes Ancol area. Yeah, and also it is close to the Bintaro. Yes, Bintaro area. Yeah, if you what is overlay with the GIS information, and you can get with area and with house, is have the effect of this subsidence itself. So, you can combine with this map, and you can see with houses is affected by this subsidence. Okay, it is the Kadoya area is also subsided. Yeah, and then one of the technique is a PS INSAR. Yes, we made observation of the Bandung city, and then it is the velocity. Yes, in millimeter per year. Yes, for example, this area is every year is 15 centimeter subsided. Yes, and here at the Yokolot area is also same. Yeah. Okay, yes, Jakarta City. Yes, it is close to the Cengkareng Airport. Yes, on the Soekarno-Hatta International Airport in the northeastern. Yes, in this area is also subsided. Every year is 15 centimeter. Yeah, and also in the northern part of the Jakarta, and here, yes, here is the Menceng or Kayu Besar. Yes, also subsided about 10 centimeter every year. Okay, yes, we also help the Malaysian government, yes, to observe the Malay Peninsula, yeah, to predict the landslide, yes, around the highway. Yeah. For example, here is the road at the Cameroon Highland. Yes, we observe using the PS INSAR, and we can get the movement of the land, yes, by using this technique, and we can predict that in the future this area is also happen the the landslide. Yeah, and we made the observation with the Malaysian government staff, and it is me and my student use the drone. It is in 2014. Yes, we already used the drone, but right now it's already it's very familiar. Yeah, but in the time is the drone itself is very expensive, but right now I think it's very cheap. Yeah, and then we extract, yes, using the drone. Yes, we can get the DEM. Yes, and then we also combine with the it is the point is from the radar. Yeah, the radar information, and then movement. Yes, we can predict it's before the movement of this landslide. Yeah. Yes, it is. We also observe close to the border of the Thailand. Yes, we visited one of the market. Yes, take a lunch. It is in the border of the Thailand. Yes, and Malaysia. And because we observe, it is in the high voltage transmission line. Yeah, because here is moving. Yes, every year is move some centimeter, and it's very dangerous. Yeah, if the tower is collapsed, it means we cannot transfer the electricity to the northern part of the Malaysian area. Yes. Yes, we made, it's very interesting. Yes, we made the observation inside the tropical forest, yes, in Malaysia. Okay, yes, this is our study site, yes, in Malaysia, yes, especially here in the high voltage transmission line. Yes, here is very dangerous, and yes, we made observation went to this area, and yes, check the condition of the tower, yes, of transmission line. Okay, yes, I think we have about 10 minutes, yes, for the question and answer. If you have the question, please deliver to me. Yeah. Okay, thank you very much, and I hope my lecture helpful for the your study in the future. Yeah. Okay, I give back to Professor Wahyudi. Yeah. Thank you very much. Yeah.
Thank you very much, Professor Josaphat Tatuko, for giving us such informative and interesting presentation. Ladies and gentlemen, now come to the question and answer session, but we have only maybe 7 minutes. So please, yeah. So Professor Josaphat, you can see the question here in the chat box. Maybe you can answer 1 or 2 questions here. So the first from Mr. Arif, yeah. Number 1, how we know about mode in any SAR satellite? For example, a loss, is it different to process SAR image on every mode? This is the first question. Maybe you can answer directly.
Okay, how to know about the the mode? Yeah, actually, when you buy the SAR image, yes, they already have the some of the file. Yeah, the file that have the information about the mode and the head, and also some of the parameter of this satellite system information. So it is I think it's no problem. Yes, or when you're searching or you want to buy the image itself, I think it's you can find the metadata. Yeah, metadata of the every image. Yes, and you can find the information of the mode itself. Yeah, and next is how deep underground of SAR. Yes, it depends on the frequency. The long wave, for example, the P band, and the P band is you can get maybe about more than 5 meter. But L band is depend on the dielectric constant, on the humidity of the land, yeah, on the soil itself. Yeah, it is maybe some meter, yeah, some of the meter. Yes, you can observe using the LOS images. But if high frequency, for example, the C band or X band, it is almost you cannot use to penetrate the land. Yeah. Okay, and then how can identify the differentiation between the volume and surface? Oh, okay. You can use the matrix. Yeah, metric of when you learn about the polarimetric SAR on the pulsar. Yeah, it is in the matrix information from the surface scattering, volume scattering, and double bonds or multi scattering, and also from the helix. It is different. Yes, a different matrix. Yeah, it is don't worry, and please learn about the polarimetric SAR. Yeah, we can observe subsidence with many methods like PN inside, and what in the best one? Yeah, okay. I think the best one is we cannot decide. Is depend on the application you want to provide. Yeah, the INSAR, PS INSAR is to know about the land deformation. PS INSAR is you want to know about the velocity. Yeah, velocity of the subsidence or uplift is using the PS INSAR. The INSAR is to know the subsidence uplift on the movement. Yes, horizontal movement. Yes, you can extract using the INSAR. Even the horizontal is a little bit difficult. Yes, because no horizontal movement. You cannot derive using the azimuth. Yeah, because the azimuth compression already extracted the movement at the horizontal. But yes, I think it's depend on the application you want to use. Yeah, if you want to know about the land deformation, horizontal and sorry, the vertical movement, I think better use the INSAR. Yeah, but if you want to know the velocity like the subsidence and the lapindo, the velocity is I think better use the PS INSAR. Okay, and then
okay, this is last question.
Yeah,
could you answer
from
this?
the Khalil Ibrahim Sang? Yeah. The application of SAR wave mode is okay. Okay. The atmospheric data. Yes. Actually, atmospheric affected is low frequency, is the affected is more. Yeah, if you use the L band, P band is I think is the the rotation angle is to be closely one of the rotation. Yes, about close to the 360 degree. Between of the rotation of the angle is you can get the information of the atmosphere. Yeah, including the humidity on the for example, the thickness of the cloud. Yes, it is you can extract using the low frequency synthetic aperture radar. Yes, like now is familiar using the L band. Yeah, but sometimes is you can use the C band, like the Sentinel-1 and Sentinel B. Is you can also use to get the information of the atmospheric data. But sometimes if we want to get the ground land deformation information, the atmospheric error, yes, effect, yes, it is a big problem for us. So in this case, is you can use the what is the filter, yeah, to filtering the response on the effect caused by the atmosphere. You can use some of the technique, yes. Atmospheric filtering, APS. Yes, APS is one of the technique. I'm sorry, I forget the CS. I think S is screening. Yeah, the screen. Yeah. Okay, there is a division between the model with a spectral. Yeah. Yes, of course. Yes, the spectral. Yeah, but unfortunately, yes, right now is every satellite is just single frequency. Yeah, but in the future, is multi spectral synthetic aperture radar is already established. So you can get the the response of the spectral. Yeah, but right now is every satellite is if you want to observe one area, of course using multi spectral satellite of the synthetic aperture is possible, but the condition of the atmosphere is changed. Yeah, so in this case is sometimes difficult. Yeah, to compare between one satellite, for example LCX band, to compare is still difficult. Yeah. Okay, of the model and start observation. Yeah. I don't know about the last apart from the observation variability by comparison of the model prediction and SAR observation. Model, it means for example in my paper, yes, you can read in my paper, for example, I'm always made the ground survey. So why the prediction using my theory and then the ground and also from the SAR. Yes, we need to compare. Like when I made the observation of the Mount Merapi, in the the error is about 0.2 meter. Yes, it is 20 centimeter error. And also I made the observation at the Lapindo. If I use the very long GPS data, it means the error is about 0.6. It's still 60 centimeter error. Yeah, but it's very short. Even it's very short event. So in this case, it's just a 0.2 or 0.3 meter. It means 20 or 30 centimeter error. It's still error. Maybe we need to consider the effect of the error caused by the system itself, by the atmosphere, and also by the humidity. And I think it's also on the multi-scattering and some of the many errors. So in this case, we must solve by one. Even the GPS itself also have some error. So it means if less than 0.5 meter, I think it's still acceptable. Yeah. Okay.
I think.
Yeah.
Okay, time is over, I think.
Yeah.
So Professor Josaphat.
Yeah.
Thank you. Ladies and gentlemen, we finally come to the end of this session. So I'd like to thank Professor Josaphat for the informative and interesting presentation, and all the participants for the very active participation. And now, before we leave this room, please take photos of us. So Miss Harmita or Rifa, could you help to take photos of us?
Okay, for all participants, please open your camera so we can take a picture together on a screen. You can say cheese or something so your face more cheerful on screen. Okay, for the first page, I will take the photo. And then the second page. And then third page. Fourth page or the last page. Thank you, Mr. and all participants.
Okay, thank you for all, and I close this session. Thank you very much. Terima kasih,
Thank you,
Pak
Professor
Josaphat.
Josaphat.
Okay, thank you very much, and keep healthy, all of you. Yes, I hope we can meet you anytime and any place. Yeah. Okay,
Maybe
thank you
it's
very
in
much.
base.
Yeah.
Thank you.
Okay.
Yeah.
Thank you. Okay, now I end this meeting for all.